Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
About waves and superposition. We define wave as a disturbance which travels through a medium and transfers energy from one part of the medium to another without causing any permanent displacement of the particles of the medium. I don't know, it wasn't you, but I think I've used this definition a number of times. It's a disturbance because once it enters into a medium, it disturbs the medium. And then when the medium is disturbed, energy can be transferred through the medium. Just imagine you dropped a piece of stone into water in a tank. The point where the water is dropped, the stone is dropped, is disturbed. Like the water was at rest, still, like we say still water, you understand what I mean? So at that point it is disturbed. Can you just focus on what we're doing? Now at that point the water is disturbed. Now what is happening, or what happened at the point where the stone is dropped? We be spreading all over the surface of the water until it gets to that point. The point I'm making is something like this. Let me see if I have if this is the surface of the water and then you dropped a piece of stone here, ripples will start forming that keeps getting wider, 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 is it not? As it spreads all around. So the wave disturbs the water, which is the medium. And in doing that, energy is transferred from that point where the stone is dropped to other points on the surface of the water. And while that is happening, as the wave is spreading, the particles of the water will be vibrating. In this case, the particles of the water vibrate. The particles vibrate up, down, while the wave is spreading sideways, isn't it? What kind of wave do we call this? Transverse wave. Okay. Now, when the direction of vibration is in the same plane or parallel to the direction of spread of the wave, what do we call that kind of wave? Longitudinal or longitudinal, So this wave distorts the water and transfers energy throughout the water. In doing so, the particles of the water will be displaced, but not permanently, because when the wave passes, the particles of the water will go back to their original position. And so we say a wave is a disturbance which travels through a medium like the water and transfers energy from one point of the medium to another without causing any permanent displacement to the particles of the medium. Does it make sense? Okay, so, but some waves do not even require a medium. What do you call that? Electromagnetic wave. So, some waves will still pass through space where there's no medium. All right, that's just the general principle of wave. But then at this point, we are looking at it much more in detail. So we talk about waves and superposition. Progressive waves are waves that are just spreading, like the water wave dropped at a particular point on the surface of the water, and then it creates ripples that keep spreading, getting wider and wider and wider. That's progressive wave, spreading in all directions, right? Okay, that same ripple I formed by dropping a piece of stone here, which created ripples that keeps expanding, ripples that keep expanding, one circle, a bigger circle, a bigger circle, and so on. You know, if he hits, for instance, the bank of the river, or maybe the wall of the container, if he hits the wall of the container, right, do you know that it will be reflected? It starts bouncing out, bouncing back, bouncing back, bouncing back. Yes, that's what happens. When a wave that created ripples spreading hits the walls of the container or hits an obstacle, it reflects and then you see it going back again. So you see that this yellow one, which actually started from this point, was traveling to the right, is it not? Was traveling to the right. The reflected one is traveling to where? The left. So these are two opposite waves, and they are climbing on top of each other, so to speak. We call that superposition. In fact, superposition is when two waves or more waves overlap. Okay? Now, when that happens, they may cause what we call constructive or destructive interference, depending on the way the waves are. So, a particular kind of superposition can cause what we call standing or stationary wave. Standing or stationary wave. So I'll zoom in a bit. A standing or stationary wave is formed when two progressive waves of the same amplitude and wavelength traveling in opposite directions. You know, like this ripple, you know, it started spreading, hit the wall of the container and started bouncing back. You get that? So the two waves were traveling in the opposite direction. Maybe I should just review some of the things I did so that you can see what happened earlier. Okay, let me see if I can take it back a bit to show you how that was done. Okay. Oh, I must have removed that, filling that. Okay, so basically what I said is a standing or what we call stationary wave is formed whenever two progressive waves, remember two progressive waves, a progressive wave is just a wave that is spreading all in all directions. Two progressive waves that have the same amplitude and wavelength, now traveling in opposite directions, superpose. Like this one, the red one, moving to, what direction is it going? What direction is the red one going? Look at it, you can see the arrow. I mean, it's going to the right now.
Yes.
The green one is going to where?
Oh, yes.
The left. Are they not traveling in opposite directions? So, if they have the same amplitude, you know what an amplitude is? I didn't need to bother you about that. Of course, the amplitude is the maximum displacement of the particles of the medium. If I wanted to use this, from here to here is the amplitude now, is it not? From the rest or undisturbed position to the maximum displacement, the distance between it is the amplitude. So from here to here is an amplitude. You know, you also know what the wavelength is. The distance traveled when the wave complete one oscillation or one cycle. From, for instance, A to E is a wavelength, isn't it? A to E is a wavelength, or C to G, or from peak to peak, B to F, or trough to trough, D to H. You know, we normally call these valleys trough, and the peaks crest. So it can be crest to crest, that's D to F, or trough to trough, D to H, you know, or a full cycle from A to E. They are all wavelength. Amplitude is this height of a wave, so to speak. The maximum displacement for the particles of the medium. That's the highest shift the particles. Like if the water was at this level, before the wave passed, like it was still water, just stationary. You know what we say, still water at rest. Now when the wave started passing, the water was jumping up, down, up, down. Now, after the wave passes, it will still come back to its original position, isn't it? So, from the rest position to the maximum that it jumped to its amplitude. Also, from that rest position to the minimum it fell to its amplitude. Okay, so if you have two waves that are traveling in opposite direction, one, say, to the right, the other one to the left, and they overlap, that's what we call superposition. Superposition is just when two waves overlap. Then if these two special waves are such that they have the same amplitude and same wavelength, they will form what we call a stationary wave or a standing wave. The reason is, at this point, you won't even notice that there's a movement, because this one moved this way and this one is moving the other way. It's almost like cancelling the effect. So the resultant displacement will be zero at every point. Because let's look at this point. The distance from here to here is 5 up. The distance from here to here is 5 down. What is the displacement? Plus 5 minus 5, 0. Plus 5 up, minus 5 down, 0. So at every point on a stationary wave, the resultant displacement is always 0. That is if it forms a stationary wave. And you know a stationary wave must have, can you give me the conditions necessary for the formation of a stationary wave?
The wave must be of the same speed.
Same speed,
Same type.
same amplitude, same wavelength, traveling in opposite direction. It must be of the same speed because it must have the same frequency. That's the only way that can happen. Okay, so I want you to, because I lettered this so that you can see it. So let me zoom it in. The conditions necessary for the formation of stationary waves are, let's mention them. A, they must be formed by two progressive waves moving opposite directions and having same amplitude, same wavelength. You know, I think we have mentioned up to, and they superpose, that they overlap. You know, because of the way they overlap, the resultant displacement is always 0. You know, and that also means the resultant speed will be 0. Because this velocity is speed over time, is it not? If speed is 0, whatever the time is, it will also be 0. Alright? That's the thing about this unique thing about stationary wave. It has a 0 speed. You know, the thing is the speed cancel out. It has a 0 displacement, it has a 0 speed. These are multiple choice questions. You know how they structure this multiple choice. That's why I'm spending time to talk about each of these things. So what is a progressive wave? Before we move on, a progressive wave is any wave that is just spreading in any direction. It could be a wave moving to the right or a wave moving to the left. Any spreading wave is progressive. You know when we say something is progressing, making movement. Now, what is a stationary wave? A stationary wave is formed when two progressive waves that are traveling in opposite directions superpose such that they have the same wavelength and same amplitude, and of course they must be moving at the same speed because they will have the same frequency. Why did I say that? If you remember your wave equation, remember our popular wave equation, V is equal to F lambda, isn't it?
Yeah.
V is equal to F lambda. Are you looking at the screen? V is equal to what? If they have the same wavelength and of course the same frequency, what does that tell you? They will have the same speed. So these are the conditions necessary for the formation of a stationary wave. Another name for stationary wave is standing wave. You know. All right. So having said that, we need to look at some of the things that will happen. Anyways, we know that from here A to E is a wavelength, isn't it? So what is A to C? Please, let's look at the screen. You don't have this. Can you fix it a little bit so that I can focus on it? A to C will be half of a wavelength, which is wavelength over. Please, you need to take note of what I'm saying. It's important. If A to E, you know A to E is a wavelength because it's a complete cycle, like a complete circle. Think of it as a circle, though what I mean is cycle. A to E is a wavelength. What is A to C? Half of a wavelength, which is, okay, lambda over 2. What is A to a position here I will call B?
Lambda over 4.
Lambda over 4. You need to take note of this thing. Oh, this is very, very important, my good friend. This is very, very important to the next thing we're going to do. This is half of it, A to C. A to B will be quarter of it, so lambda over 4, because the wavelength is 1 lambda. So what is A to G? What will A to G be?
1.5.
Let's see what A to G is. This is
1.5.
A to E is a full lambda. So A to G must be lambda and a half lambda. So 1.5 lambda. Or 1.5 is one whole number, 1 over 2, which is 3 over 2 lambda. So this is 1.5 lambda if you like. Or 1 whole number, 1 over 2 lambda. Or 3 over 2 lambda. Did you understand what we did? That is important because of the next thing we're going to do. There are many ways stationary waves can be formed. Wave is such an interesting topic because it applies in so many things. You know, for instance, if you have a string attached to two ends like an A and an B, and then you plug the string. Like if the string is taut, you know what I mean by taut? T-A-U-T. Tensioned. If it is tensioned, like if it is tension, and then like tension means stiff such that it's not slagging. It's tension, you know, tension. Then you plug the string, like the guitar, the violin, those string instruments. If you plug it, you know, it will be vibrating. This is the string. It was originally like AB, just like the length AB. And it is plugged. You know, it will go up, go down. So it's actually forming a wave that goes, hits here, bounces back, hits here. Goes, hits here, bounces back, hits here. Goes, hits here, bounces back, hits here. That's actually why it produces a sound that you can hear. What is sound, by the way?
Sound.
When is sound produced?
Vibration of the.
Good. Sound is produced whenever an object vibrates. It doesn't mean that you must hear it, because there are certain sounds that have frequencies that you may not be able to hear, which are called ultrasound. But generally, sound is produced when an object does what? Vibrates. So this string that was initially the string was tensioned like a guitar, just lying along AB, like this red line. But when you plug it, it goes up, goes down, like it is vibrating. Up, down, up, down. So that vibrating sets up a wave. It sets up two progressive waves. Are you getting what I'm saying? Because the first wave goes to the right, hits this exactly, hits this fixed position, reflects to the left, reflects again to the right, and so on, and so on. So it forms a stationary wave. By the way, for a stationary, whenever a stationary wave is formed, these points are what we call nodes. You see these points? These points are called what? Nodes. These are nodes. A and B are the nodes. By the time you start seeing multiple choice questions on this, you'll be you know what I'm talking about? Yeah. So you need to take note of this. That's why I'm taking my time to talk about them like this. So in between nodes, we call them what? What do we call in between nodes? We have A to B, and sound energy is produced, which has set up vibrations in the air because of formation of compressions, rarefaction, compression, rarefaction. And the air particles are vibrating in the same direction as the wave is spreading. In other words, the direction of vibration of the air particles is parallel to the direction of the spread of the wave, isn't it? That's why it's a longitudinal wave. Okay. Now, assuming this particular one produces this kind of wave that strikes the other fixed point and reflects, we can see that the length of this string, is equal to what wavelength? In terms of wavelength. What is this in terms of wavelength?
With lambda over 2.
This is half of the wavelength. Because the full wavelength would have been all up to here. So this is length, lambda over 2, right? Good. You'll be seeing questions like this. So this length is equal to lambda over 2. In fact, it is this that can produce what we call the fundamental frequency, the very first frequency. Very first frequency can only be produced when it is lambda over 2, or what we call the first harmonic. I will explain that later. So now, if this string did not go like this and then bounce back, if it went this way and then bounce back, what is this length in terms of the lambda? This length is lambda. Now this one is produced by a different frequency, which we call second harmonic. I'll talk about all that. Of course, it can also go this way and then bounce back. And as you can see, this length is equal to how many lambda? 1.5. That's this length is 3 lambda over 2. Or you can make lambda a solid formula, 2L over 3. In all these cases, you can still make lambda solid formula. You can make lambda solid formula. Okay. Another case is when it produces an effect like this and then bounces back. In this case, you have one lambda, 2 lambdas, is it not? So this entire length AB is now 2 lambdas. So lambda itself is L over 2. So the first frequency that can ever happen with a string fixed at both ends is the fundamental frequency, and we have a wavelength equal to 2 times that length. I will explain that. If you tie a string from one end to another end, the fundamental frequency, if you plug the string, the frequency of the sound wave must have a wavelength equal to 2 times the length of that string for the first frequency that will be produced, depending on the way you plug it. There's also a way you can plug it such that the motion is this way. In that case, it will produce a frequency equal to just the length of that string. It can be plugged in a particular way that it will produce a frequency equal to 2 times the length of the string divided by 3, or 2/3 of the length of the string. In this case, it produces a third harmonic. They will sound differently. That's what I'm saying. You know, frequency determines pitch. If something has a different frequency, it means it has a different pitch. So that, you know, there's a way you will plug a string, and if you hear a particular sound, there's another way you plug it here, depending on, and then the fourth harmonic is this one, which the lambda, the wavelength itself will be that length, half of the length. Okay, let's see how this plays out. An example: a string of length 200 centimeters is tied at both ends to produce a third, that's a tension string. Calculate the first frequency, that's the fundamental frequency, when the first resonance is heard in air by plugging the string. The first frequency. Yeah, and we know the speed of sound in air, about 330 meters per second. You know the speed of sound in liquid, about 1,500 meters per second. The speed of sound in steel, but it's in air. So we're using the speed in air. I know V is equal to F lambda. So F is V over lambda. And you know for the first frequency, that's that fundamental frequency, the lambda must be equal to what? 2 times the length. For the fundamental frequency, the lambda must be, the wavelength must be equal to 2 times the, yes. Are you in agreement? So 2 times the length, that's 2 times 200, that's 400, isn't it? So the wavelength must be equal to 2 times 2. Because if you change this, or you work in SIN, the speed is given in SIN is 330 meters per second. So the length must also be changed to SIN 3 meters. So this will be the fundamental frequency of that string, which is the first frequency. Or what we call first harmonic. Now, for that same string, calculate the second and third harmonics. There's a reason for asking you to do that. I want you to notice something. Remember the value we got for the first frequency, 82.5 Hz. Let's calculate the second. You know, the second harmonic is when lambda is L. You can recall when lambda is L, that's the lambda is equal to the length of the string. So that means the second harmonic will be also 320 over lambda, and the lambda is just the length. And remember the length of that string is what? 200 centimeters, which is 2 meters, right? So 330 over 2, because 330 is the speed in SI. So that gives us 165. If you get the third harmonic, that's the third frequency that can be heard to produce a resonance. It will be 330 over 2 times the length. If you notice, the lambda is 2 times the length for the third harmonic. The wavelength is 2 times the length. 2 times the length divided by 3, I mean. We found it. Music. You see that the frequency will keep increasing. Like this one, the first harmonic we got 82.5. That's how we call it the first frequency. The second frequency is bigger, 165 Hz. The third one, from my calculation, 330 over 2 times 2/3 of the length. Am I making a mistake? Where is the, for the third frequency? That's 2L over 3 now, you know? 2L over 3. And the length is 2 meters, so 2 times 2 over 3. So we are right. 2L, this is 2L over 3. And this gives us 247.5. So now let's see the way it is. The first harmonic was 2.5. Second one was 165. Third one was 247.5. You want to use a calculator to check the ratio. Reduce this to the simplest form. 82.5 for the first one, ratio 165 for the second one, ratio 247.5 for the third one. You know, you divide up through by the smallest. Everything divided by the 2.5. 1:2:3. How did I get this, by the way? You divide it by 82.5, this divided by 82.5, this divided by 82.5 to get it in the simplest form. So that's 1:2:3. So if a string is tensioned at both ends, the frequencies you will get from the string within the whole integer multiples, you know, whole number integers, 1:2:3. The next one will be 2 times the other one. The other one will be 3 times the first fundamental frequency. The next one will be 4 times the fundamental frequency. The next one will be 5 times. So 1:2:3:4:5 for a tension string. Right? Yes. Okay. It doesn't matter what the length is. If you do it, you will get the same thing. For instance, if we change the length to 300, that's if it's now 300 centimeters long, which is 3 meters. If you do the same thing, the first one will be 55. Second harmonic, first harmonic of fundamental frequency is 55. Second harmonic is 110. Third harmonic is 165. And if you divide by the smallest, You will also get 1 ratio 2 ratio 3. The next one will also be 4. So in whatever form, that's the way it will be 4. A string that is fixed at both ends. Now, that is one way a stationary wave can be obtained. A stationary wave can also be obtained in a pipe, whether it is a closed pipe or an open pipe. So the ratio of frequencies, fundamental harmonics obtained from any given string which is tied at both ends forms a whole number integer. 1 ratio 2 ratio 3 ratio 4 and so on. So F fundamental ratio, the second one will be 2 times the F fundamental. Ratio, the third one will be 3 times the F fundamental. The fourth one will be 4 times the F fundamental. So that's for string. And that's what we explained here. FO, 2FO, 3FO, and so on. It's not only in string that you can produce this. Some of these things are questions you can attempt. Now, if it is a closed a pipe, let me see where I discuss this pipe in details. Okay. Let's see this. Let me zoom it in. By the way, a pipe can be closed or open. Closed means one end of it is closed. Open means both ends are open. Closed, like a closed pipe, means one end closed, the other open. But if it is open, both ends are open. For instance, if it is a closed pipe, you know, one way a resonance can be formed is when a wave enters in, hits the closed thing and bounces out. It enters in, hits this and bounces out. It enters in, hits this and bounces out. What is this? You know, this is the length of the pipe from here to here. Pardon?
Resonance increase.
Well, resonance, there are many ways I can define resonance. Resonance, of course, one way resonance can occur is when an object is vibrating at a particular frequency close to another object. Like I'm an object vibrating at a particular frequency. Let's say 20 hertz. How many hertz?
20.
Now, if I'm vibrating close to you, not necessarily touching you, close to you, if your natural frequency of vibration is 20 hertz, I can set you in vibration without even touching you. Just by my own vibration, I set you into vibration.
Why?
Because my frequency is close to your natural frequency. So that's resonance. And that is why if you carry out this experiment with a tuning fork, let me tell you how that happens. So that you understand the resonance. When you hit the fork, like you hit it on the table and bring it you hit the fork, tuning fork, you hit it to produce a vibration. You bring it close to the opening part of the pipe. At every point where it produces a resonance, you will hear a louder sound. You know, when you hit a fork, I had one for a long time at one time. If you hit a tuning fork is just like 2 prongs. You know, you hit it to set it to vibrate. You won't hear anything, it will still be vibrating. But anytime it produces a resonance by bringing it close, if you bring it close to an open pipe, and at the time it produces a resonance, you will hear a sound. Like that, what's it called? Whizzing sound will be more pronounced. It's not in all cases that it will produce a resonance. Now, this is the way we do this. I think I need to explain this to you. Usually, when you want to carry this practical, this is the way it is done. You fill this pipe with water, for instance. There's a question like that I'm giving you here. Maybe with a tap. And then, you know, there's water here. And then you get your tuning fork. 2-prong tuning fork. That's the tuning fork. Are you getting this? You hit it on a table to set it into vibration. Then you bring it close to this place. While this water is dripping gradually, it will not set up any resonance until the vibration itself can hit and come back like this first resonance.
Really?
And let me say that again, and I will explain it. You know, the level of the opening will be changing as the water is draining. You know, the water is draining out. This length will be increasing, isn't it? It doesn't produce resonance until the sound wave in air is able to hit here and bounce back exactly the way this picture is. This picture. You can now ask me your question. Exactly the way this picture is. If you can hit it and bounce back exactly the way this picture is, it sets up the first resonance. You will hear a frequency. Then you will continue to, after a while, when it does that first one, and the water is dripping, you know, the length of the exposed thing will be changing again, is it not? You won't hear anything. You won't hear anything until it gets to a particular point. First of all, let me even draw the way the first time it produced the resonance was when it was like this. Was when the wave hit here and bounced back. Exactly like this. Such that the distance from here to here is what in terms of wavelength?
What is this exposed length in terms of wavelength?
Exposed length.
Yeah, this length in terms of wavelength.
Oh.
Yep. What did he say?
No, is it one?
No, I mean just the length. You remember when you're talking about it? First of all, let me help you to appreciate it. You know, the whole thing would have been like this. I will clean it up.
Okay.
This is how the full wavelength would have gone, isn't it?
Oh, is that? Oh, yeah.
That's why I had to take you through that at first. So what's the length of this exposed part from here to here in terms of wavelength?
Well, isn't that just like a quarter?
It's just a quarter. It's exactly a quarter. So this length is just a quarter of a wavelength.
Yeah.
It's just a quarter of a wavelength. So at that particular point, it will produce resonance. Now, this is what you will notice when you are carrying out the experiment. Are you listening to me? You get a tuning fork. A tuning fork is just a fork with two prongs, you know, like normal fork we use for, you know, cutleries.
Yeah.
So
Yeah.
it has two prongs. You tap the tuning fork on a surface, like on your table, just to set up vibration. You know, sound is produced whenever an object vibrates. So you just hit it so that the prongs will be vibrating. The two prongs of the tuning fork will be vibrating. You may not even hear anything. In fact, you won't hear anything. Usually you won't hear anything until you bring it close to your ear. But see, this is how we do this. You tap the tuning fork on the table, and then you bring it close to the mouth of this thing. So let me put up a diagram to show you what I mean. So yeah, I'm going to help you to work very well with your imagination. I know you carry out this experiment. This is a tuning fork. First of all, we set it into vibration. How did we set it into vibration? Hit it on the table. Hit it on the table. We set it into vibration. So as it is vibrating, of course, this water will be draining gradually. Maybe you started from the top. It was probably filled to the brim of this test tube or this pipette or whatever. Is this one burette or pipette? I don't know. You forgot your chemistry.
Is it not a pipette?
What? Okay. All right. So as it is draining, you know, more depth will be. It will getting the exposed part will be getting deeper and deeper and deeper. Am I right? As it's draining from when it was filled to the brim. Once it gets to a particular point, like here, where the wave from this your tuning fork hits the surface of the water and bounces back like this, it will produce the first resonance, the first fundamental frequency. And then you are going to hear the sound that you were not hearing before. In fact, that tuning fork that was vibrating that you couldn't see, that was producing a sound, will produce a loud sound you'll be able to hear. I mean, an audible sound. It will just make the first audible sound you will hear. So this is the point. As I reiterate this water was filled to the brim, and then we set the tuning fork into vibration and brought it close to the lid of this tube. And then we allow water to be draining gradually. As it is draining gradually, wave will be coming in, but it may not strike it and then return in such a way that the length is exactly a quarter of a wavelength. It is when it is exactly a quarter of a wavelength that it will produce the first resonance. So the sound will be loud. You just hear it immediately. Okay, you take note of that, and then you start draining again. Let me show you one more. There's a particular position it will be such that the wave will come in like this. So this new length, what's this new length in terms of a wavelength? Sorry, let me draw it. What's this new length in terms of a wavelength? This new length of the exposed part of the tube after more water has drained out. It's not exactly half. You know, the full wavelength would have come up here to complete itself. If I can I draw the central. Let me show you the central on the stop position. On the stop position would have been like this, right? As it's shown. So the wave will go like this and come back to complete here. You know, this is a sketch. The real diagram would have been much better. Perhaps it's me that is confusing you. So let me draw it better with something that will show exactly what I mean, please. I'm sorry. My drawing should be better than this. Very quickly, please. Very quickly. I broke my promise. Okay, it went this way, So consider the on the stop position to have been like this. So I'm asking you, what's the distance of this exposed part of the tube in terms of wavelength? If you notice, the full thing would have been complete if it had gone up and landed here. But this is where we are from here to here. Are you still with me?
Yeah.
Okay. So a little thinking. I can zoom in to make this thing bigger. Let me zoom in. Yep. So the question again is, from here to here is what in terms of a wavelength?
Words. From there to there, 1.5.
You are almost right. See, if I started from, let me call here A. Are you there? Have you seen where I started as A and moved like this? Tell me, what is this in terms of a wavelength?
Half.
It's not up to, yeah, that's half. Yeah, you are very right. From here to, if I can write letters, this is B. A to B is half. So B to C is what?
B to C is 1.5.
It's not 1.5. B to C
Oh,
is just a quarter because
yeah, 1.25.
it's a quarter. B to C is just 1/4. You mean?
Yeah, yeah, yeah.
I meant B to C is just a quarter because it would have been at D that it would have completed another half. In fact, what I'm saying is A to B is half, or A to B is half, then B to D would have been another half. So A to D is the full wavelength. A to D. Check it
Is that
out.
what I said at first and you said no?
But I was asking about the exposed length. The exposed length did not get to where the wavelength completed itself. It's just from here to here, from C to A. Now the question is, what is C to A in terms of a wavelength?
A is 3/4.
3/4, because a half and a quarter, that's 3/4. So this is 3/4 of a wavelength. It is in this position that it will produce another loud sound, which will be the second fundamental frequency, and the second harmonics, or the second resonance. We can go on and on and on and on and on and discover. Okay, please, for the sake of explanation, you just get the last one and then you compare. Please, just the last resonance, because at least it will help us to compare. The last resonance, assuming the water level is now here. You see where I am?
Yeah.
Okay, so let me just draw the on these top positions because it will help us to see it better. Please bear with my rough sketch. So I will call here again K. Okay, another letter. Marker should be better. K, L, M, P. Okay, where would have stopped? Somewhere here, P. So what is, the exposed length is just from here to here. The new length now. So what's this new length in terms of wavelength? We can count. K to L is half, is it not?
Yeah.
K to M is one full wavelength, is it not?
Yeah.
Okay. Maybe L to M to N, which is actually L, before P. So this is one full wavelength, K to M plus a quarter. Am I right? This is a quarter now, isn't it?
Yeah.
1 1/4. That's 5/4. So that will be 5/4 wavelength. Do you want to confirm that?
5/4. Yeah.
Yeah, that's 1 1/4. That's 5/4 wavelengths. So that's 1 1/4 wavelength. That's the length of L. Is 1 1/4 wavelength, or 5/4 wavelength. Okay, I think this should be good enough for us to summarize. So the point is, the first frequency, if you remember, was I claimed it. Okay, let me leave it here, please. The first resonance or first fundamental frequency was when it was this way. It just did this and went up. This was the first one, where L was what? A quarter of a wavelength. Do you remember?
Yeah.
The first one was when the exposed length was a quarter of a wavelength. The second one is where the exposed length is 3/4 of the wavelength. The fourth one, the second is 3/4 of the wavelength. The third one is when the length is 5/4 of the wavelength. Okay, so in summary, let's go to the previous page so that I don't have to overflow this matter.
Yeah. What the next?
No, the previous, please.
Yeah, with the previous one.
Okay. So you will see that now have a particular closed pipe, maybe 3 different closed pipes, the first, the second, and the third. Now what I mean is 3 different closed pipes but of the same length of a column, the distance from A to N is the same as this for all 3. So we are not going to vary the length of the exposed part of the tube. Is the same length for these 3 different test tubes or closed pipe. Remember, it's closed because one end is open and the other ends are closed, so now if we have these 3 different closed pipes of the same length of exposed length of air column, and then we produced sound of different frequencies. Maybe we have 3 different tuning fork. The first tuning fork produced a particular frequency that caused sound to move in this way. Another tuning fork of a different frequency produces a sound that moves this way. Yet another tuning fork of another frequency produces sound that goes this way. All of them having the same length of exposed air column or length of air column. But then of course there will be different frequencies that can produce these different motions of sound wave. Of course, this first one, which will produce the fundamental frequency, will be the lowest of the frequencies. You can see that this frequency is lower than the second one in the middle, and this second one in the middle is still lower than the third one at the other end. The highest frequency is this one. The one on the right is the highest frequency. The lowest frequency is the one on the left. So now if we have these situations, of course we can see that in terms of the wavelength, this length, because it's the same length, the distance from here to here is the same length of the exposed column. Unlike the other one that we were varying the length. If you remember, we were changing the length of the previous example. But in this case, we kept the length the same. So in terms of the wavelength, this first length is equal to 4 times the wavelength, because the distance from here to here is 1/4 of a wavelength. So it's 1/4 of a wavelength. So the full wavelength is 4 times this length. 4 times this length, that's actually what I mean. For this particular frequency, of course, that will produce the fundamental frequency. Now the second harmonic, or the second frequency, which we actually call the first overtone in musical terms, the second frequency or the second harmonic is called the first overtone. The third frequency or the third harmonic is called the second overtone. So that's for music. Now the second harmonic or the second frequency, the length in terms of the wavelength is 4L/3, as you can see, because this is half of a wavelength, this is a quarter, that means L is 3/4 of wavelength over 4, just like L in this first one is quarter of a wavelength. In this second one, the length is this same length, because the same length we're using in all cases, this same length, that's the length of the exposed length of air column. For the second one is 3/4 wavelength, and the fourth one is of course 1 and 1/4 of a wavelength. So by the time we make wavelength subject of formula in this first one, we have wavelength equal to 4L. If we make wavelength subject of formula in this second one, we have wavelength equal to 4L over 3. If we make wavelength subject of formula in this third one, we have wavelength equal to 4L over 5.
That would be.
Try and get the frequencies. Speed V is, frequency is speed over wavelength, speed over wavelength, speed over wavelength, isn't it?
Yeah.
So the fundamental frequency, because it's all about fundamental frequency, the fundamental frequency is speed over the wavelength, and the wavelength is 4L for the first frequency.
Yeah.
So V over 4L. The second, that's the second one, will be V over the wavelength, and the wavelength is 4L over 3, 4L over 3. So you do V over 4L over 3, mathematics. V over 4, V divided by 4L over 3 will eventually give you 3 V over 4L.
Yeah.
The fourth one, which is also V over wavelength, I mean the third one actually. The third one, which is V over wavelength, is V over 4L over 5. And that will give us 5V over 4L. Just simple arithmetics. Anyway, the point I want you to notice is the first one is V over 4L. The second one is 3V over 4L. The third one is 5V over 4L. So you notice the ratio. All of them have V over 4L, V over 4L, V over 4L. So what's the ratio?
1:3:5.
Yeah, 1:3:5. So the next one would have been 7. So for a closed pipe, the ratio is odd numbers, 1:3:5. I think that's what we call odd numbers.
Yeah.
Okay, 1:3:5. So if the first one is F0, that's for a closed pipe. If the first one is F0, the second one will be 3F0, the third one will be 5F0, the next one will be 7F0, and so on. If you try it for an open pipe, you will get a different thing. But that, if in fact, an open pipe will produce whole number integers too, like a string. But we can't disturb ourselves about that. So in our next discussion, we're going to look at examples, how these things apply. Okay?
Yeah.
Okay, please, like some of these examples you can see here, if you check through these, that's part of the things we'll be looking at. The other ones here, they give you these, ask you to find these, find a particular thing that will produce this and all that. So we'll be looking at that later. All right, I think this should form a good foundation for subsequent discussions. Okay? So.
Okay.
All right. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.